Today is the ultimate proof technique, and this proof technique is going to be a lot more useful than you might think at first, since I would say the majority of proofs are proof by contradiction. Here's the general layout for a proof by contradiction. Say we want to prove some statement phi. We assume not phi, and then we have to show that there is some contradiction eventually that says psi and not psi. If this happens, we say that our assumption would be false, which would give us not phi, and we know this is equal to phi, therefore we have proven the statement. And you're saying, what is psi and not psi? The thing is, we don't know what those are going to be ahead of time. You have to sort of have a general idea of what you're looking for in order to make a correct contradiction. So, I'm going to do a very classical example to show you how this works. And some of you will hate me because you've seen this before. So, oh well, too bad. Learn it again. We want to show that the root of 2 is irrational. So this is difficult because we don't have any if-then statements, so a direct proof is kind of difficult. And a very good way of doing this is say, suppose you have a definition. Just saying by definition, if you have one, is fine. However, we don't. So the only real way we can do this is if we say, okay, well, assume that root 2 is rational. Okay, now where do we go from here? Well, you have to remember that root 2, or any rational number, can be rewritten as a over b, where b is not equal to 0. Okay, so this is a little bit better, because we have a definition of a rational number, so we can use it. Now let's play around algebraically with things. Okay, let's square both sides. So we have 2 is going to be equal to a squared over b squared. That's not bad, so now we can write 2b squared is equal to a squared. Now, here's a little interesting fact. Because 2b squared is equal to a squared, we can conclude that a squared is even, which actually concludes that a is even, since the square root of any even number is going to be another even number. So, because of this, we can say that, okay, a is equal to some number 2 times k. Okay, so we'll rewrite a, so we'll still take our 2b squared, and we will rewrite it as 2k squared, which really is going to be the same thing as just 4k squared, so I will write it like that. And now, b squared is going to be equal to 2k squared. Oh look, this is the same situation we had over here, except now we have different variables. So what can we conclude from this? Well, that means that b squared is even, which means that b is even. So we've done a lot of this. We know a is even, and we know b is even, but there's one little thing that you should know about rational numbers, is that when we write it as a over b, we say b is not equal to 0, and it's in lowest terms. And by lowest terms, I mean it's reduced to the simplest fraction as possible. However, if a is even, and b is even, then we have some 2k over 2j, which can be reduced to k over j. And what this means is that our number a over b here is not in lowest terms. But in our assumption, we said it was in lowest terms. And now after doing all this proof stuff, we found out it's not in lowest terms. So this is our contradiction. Our lowest terms here is our psi. We found out that it was not in lowest terms, which was our not psi. And our assumption, so we have to show root 2 is irrational, which is our phi. Our root 2 is rational is our not phi. So we have here, if we have not phi, then we get psi and not psi, which means that we get not phi, which is going to be equal to phi. So we've actually proven that root 2 is irrational. So that was a little bit crazy, I know. You might be thinking, well, okay, how do I do this with other proofs? What exactly am I supposed to do if I have a question that is not along the lines of showing root 2 is irrational? What if I do root 3 is irrational? Why isn't it the same method of proof? And the idea is that the contradiction you're looking for is going to change, and that contradiction is not always obvious. But I will give you a few things that you should be looking for. If you want to do, say, an A equals B proof, well, what you should do is you should assume A is not equal to B, and then you will eventually show that, well, maybe one of them is equal to each other. And you might get a nice contradiction that way. Or what if you have an A is equal to B proof? Well, there are ways you could do this. You could say, okay, well, assume A is less than B, and assume A is greater than B, and show that both of these get contradictions. Then the only thing that's possible, that's remaining, is that A is equal to B. So that's a little bit cool. And of course, perhaps you don't want to do contradictions, instead you want to show it directly, then you could show that A is less than or equal to B, and A is greater than or equal to B, and if something is less than or greater than, or less than or equal to, and greater than or equal to, it must be equal to. So those are different ways you can do for an A equals B proof. What if you want to have an A less than B proof is fairly straightforward, since you just show that B cannot be greater than or equal to A. Similarly, the other way is also fine. Assume that, okay, what if you have an if x then y, then not y arrow, not x? That would be a bad example. What if then y prime arrow x prime? You have something like this. Well, you could assume this, so you assume that x arrow y is true, but then you assume not this statement for a contradiction. So that is a little bit different, because what you'll find then is you'll find a contradiction in your x arrow y assumption. So there's a lot of different ways to do proofs. Obviously I can't cover everything because a lot of proofs still haven't been done in math. Fun stuff. Tons of proofs still haven't been done. Some of those are very difficult contradiction proofs. Some of them might be nice contradiction proofs that just haven't been looked at. Some of them might be proof by cases, induction. The whole point is that these proof techniques are techniques. They are not, and I will say, they're not instructions on how to prove something. They are tools, that is it. You have to pick them intelligently, and you have to fool around with some of them. You're not going to know how to prove everything the first time you do it. In fact, there are things I still don't know how to prove. There's a lot I don't know how to prove. I'm not this master proof-tician that can see a problem and say, I know exactly what to do. There's a lot of problems I can see and say, hey, I've done something like that before, and this method worked, so let's try it out. But the important thing to know is that you're going to fail. And that is okay, because you're going to get a lot more practice by failing and seeing what doesn't work than by constantly only learning the right thing, because then when you do a proof you've never seen before on an exam, you don't have any reference points of what you know doesn't work. You'll only know what does work for something similar. And when you try that method, and you find out that the one thing you tried that worked for something similar doesn't work for the proof you're doing now, doesn't work, you're going to be lost. Straight up, I'm going to tell you that this proof for root 2 is irrational. The proof I gave you does not work, and it does not work for root n is irrational for any n greater or equal to 3. It does not work. If I were to say prove root 3 is rational, the proof I gave you for root 2 will not work for root 3. In fact, what you need is the well-ordering principle, which I guess I should write it out in full. It's the well-ordering principle. And that will work for proving root 3, root 5, root 7, root 11, root 13, root 17, root 19, root 23, root 29, and so on and so forth. Anyways, that was proof by contradiction. That was the entire proof section, I believe. Yes, that was the entire proof section. So now you know how to do proofs. You'll be seeing them a lot in mathematics. Of course, discrete mathematics is not the only place you'll see proofs. Oh no, it's just the beginning. It's just the beginning of a long, painful journey of mathematical proofs. Anyways, hope you enjoyed it. If you have any other questions or have something you don't know how to do, just leave it in the comments and perhaps I can give you a hint of where to start.